Yeah, so the title of my talk is Playing to Win, Success of CADIA's General Game Playing Machine. But so I have limited time. I will mainly tell you what general game playing is and how this features in AI. This is the outline. So traditionally in AI, when we did game playing, that is, build a machine that plays a game, then we were very focused on game-specific programs, so these so-called one-trick ponies, so programs that can play one single game. Like you've seen Deep Blue, this big machine that can only play chess. And it's not just that the programs can only do one thing. Also, to make such a program, we need lots of expert knowledge. So to build Deep Blue, there were lots of expert chess players involved that told the programmers how they play chess and what are good and what are bad moves in chess. So the intelligence there doesn't really lie with the program, it lies with the programmers or the people that made the program. And so in that sense, such a game-playing program isn't really intelligent. Now, in general game playing, we try to take this a step further, so introduce some intelligence into the program. And one idea is that we try to make a program that can play arbitrary games, not just a single specific game. And this prevents us as the programmers basically from putting any knowledge about the game into the program because we don't know which game the program will be playing. So the program cannot rely on human expert knowledge about the game, on human expert players, for instance. Now, so this is a picture of how a general game playing machine could look like. At the moment, we don't really do things like this. We don't have robotics involved, and we don't actually play actual board games, and we play this in a simulated environment in the same way as you would play board games if you play them on your computer, on your iPad or something. But the idea is that we have a program that can play arbitrary games. We don't have to change the program, we just have to tell the program, this is the game we're going to play now, and then the program can play the game and can play it well. So this idea of general game playing has arisen actually pretty early with the first published work in 1968 by Jean Petrat, and later on by Bernard Pell, who did his PhD on this topic. And since 2005, there's more of a research community in this area, and we have an annual world championship, international competition where these general game playing programs play against each other, and we try to find out which one is the best, which one can play most games well. So CADIA Player is one of the players in this competition, and CADIA Player has been developed here at Reykjavik University, and it's one of the best players in this competition. It's one of two players that has won the competition 3 times now. So it's a 3 times world champion. It has also won one of the side competitions on imperfect information games, and games with hidden information like card games. So we can say that Reykjavik University is at the forefront of research in general game playing. Okay. So but how does this actually work? How do we play a general game? And I just want to demonstrate how we humans do this with a little example here. So we've probably all seen this. This is tic-tac-toe. We have 2 players, one making X's, the other O's, and both players try to get 3 in a row, either horizontally, vertically, or diagonally. So let's assume we're in this situation here. So obviously it's O's turn. His X has moved twice already. So it's O's turn again. Now, what should O do? Right? You can look at the situation and try to figure out what is a good move for O to do. And we, as we know this game, we know this is symmetric, so it doesn't really matter which of the corners we pick if we pick a corner, or it doesn't know which of the 4 side squares we pick if we pick one of those, because this is symmetric. So we really just have to look at 2 options. This is already one piece of knowledge we have about the game that we can use. And so then we have these 2 situations, and we can think of, okay, let's suppose we take one of those moves. Suppose we take one of those side squares. What happens in that situation? How does the game continue? Well, so in our mind, we make this move, and then we see, okay, now we have 2 in a row, and now X has to react to that. And the only thing X can really do at the moment there is to block this, right? To block our 2 in a row. And okay, but that creates a situation where we have to block. And okay, so this looks complicated, where we don't lose immediately, and we don't win immediately. This can continue on for a while. Okay, so let's look at the other option. Remember that this is a situation where we don't know what will happen in the end. So let's look at the other option, take a corner, and there we see, so X has to, again, block our 2 in a row. And what happens next? Okay, now X, we have to block X at either one of these 2 positions here, but we can't block both. So in the next move, X will win no matter what we do. So this is a lost situation. And so we can say, okay, because we lose on this side, it's better to do the other move no matter what. Like, we can't get worse than doing this. Yeah, this is a way of playing the game, thinking about what is the future of the game look like? What happens if we do certain moves, and how will the opponent react to that? Right. Now computers play games in pretty much the same way. What we do is so-called game tree search. So we start with the current position of the game. We think of what do the next states look like? What moves can we do? How will this affect the game state? And we do this a few steps into the future, but we can't, in general, do this all the way to the end of the game because we only have limited time to think about this and only limited memory to keep track of all these positions. So eventually we'll have to stop, and then we have to somehow evaluate a position where the game is not over yet. And we have to say, okay, does this look better for us or better for the opponent? And so this is the traditional way of playing games with a computer. We look ahead for a few steps, and then we evaluate these positions there using some form of expert knowledge that tells us, is this a good or a bad position for us? And this tells us which way we should go. Now, an alternative way, and this is what CADIA player did as the first player in general game playing, an alternative way is to not actually evaluate these positions with expert knowledge, but continue playing to the end, but only random moves. So only simulate the game to the end randomly and do that often. This way we don't have to look at all of the positions. We look only at a few random possible continuations of the game. But from this we can collect statistics to tell us how often will we win if we start in a certain position. How likely is it to win from there? And this information can be used to decide which move is the best or is likely the best. So this approach has the advantage that we don't need expert knowledge. The only thing we need is the rules of the game, so we can predict what the game will look like in the future when we do certain moves. So this is the approach how computers play games and how CADIA player plays games. There's of course a lot more to it. We can bring some knowledge into this, and we can make the computer program learn things about the game while playing the game. But I also want to tell you what this is good for. So this is not just about playing games, of course. We eventually want to solve real-world problems. And so one domain where this might be useful is general autonomous agents. So whenever you have a robot or some software agent that does something for you, this agent has to act in the environment. And just to name a few examples, you have these robotic cars, self-driving cars. They have to act in some environment, have to interact with the environment, anticipate what humans in the environment or what other agents in the environment are doing, think ahead and know beforehand what they will be doing. Or last year, Amazon got a patent on anticipatory shipping. So they'll be shipping packages to you before you know, or before you actually order the stuff. They'll just figure out what you want to order before you have figured it out. So this anticipatory shipping agent, this has to be automated, of course. This has to somehow learn what you want to order, and also has to learn like when Amazon should ship that and which way it should ship that to minimize costs and so forth. So this is an agent acting in some environment, and the environment changes all the time. There are new customers, your preferences change, shipping routes change, and so forth. Products change. Another example would be automated stock trading, where you could think of an agent handling your stock portfolio, and selling and buying and so forth. And it has to act within the rules of that we set for when you're allowed to buy and not doing insider trading and all these things. So all of these are agents that are supposed to achieve some goals, that have to react to the environment, anticipate the behavior of other agents and humans in the environment, and that have to be safe and follow the rules. So in that sense, they are much like game players that get a set of rules that have to achieve their goals and within those rules, and have to react to the other players. So in general game playing, we study the design of such systems. And of course, games are an abstraction of the real world. They are a lot simpler, but they give us some insight into how we can design agents that solve these problems. So to summarize, general game playing is a step towards general intelligence, general artificial intelligence, in the sense that we're not trying to build a single trick pony. We're trying to make a system that can solve a larger variety of problems. We are quite successful here at Backgammon University in this, and there's lots of things to do in the future where we can still extend this. We can add games of chance, hidden information, real-time games, or actual playing physically. Okay, so where we add robotics and vision and so forth. And one of the things we'll see, which can be seen as an extension of general game playing, is the general video game playing, and Julian will talk about this after the break. So this introduces some more challenges to the problem in the form of real-time requirements. Okay, thank you.